Lecture 1, Set 3, now that we've talked about what can be done with System Verilog, what are some of the career paths you could take by this knowledge? And this is, just a very tentative list based on the observation of who from our previous graduates and from all the years I've been teaching this course got job and, is useful to the industry. You could actually go into the system architecture mode, like, in previous set, I showed you a Snapdragon whole chip system. In order to design that, you need to have an understanding of the whole system. For example, where the processor goes in, where the memory goes in, and where all the peripheries go in. We need to know the performance and power architecture, profiling, and exploration. You need to do system C-based model development and validation. But the front-end design is when that is the slide with the Snapdragon that we had earlier. Let me go back here. So to give you a sense for this, is, you see this architecture level design, which is system level design. But now, if you want to go through the blocks that go inside one of these architecture and look inside those blocks, then we get into the microarchitecture. And this microarchitecture can be designed in two ways. We could look into the front end of this design or the back end of this design, which is more on the physical layer. So, coming back into, into the microarchitecture level, we could develop these designs using HDL, such as System Verilog, but we could also contribute to back-of-the-envelope timing analysis, area and power reduction, and then design verification is also mostly, done at this level, although the verification, as we will see, shall be done at each and every level. Then another possible career path is to become an implementation engineer, where you go through logic synthesis. I have to say, synthesis of logic, unlike compiling of software, which is typically done in a batch, is usually an iterative exploration. We need to go through this multiple times to make sure that we get the timing closure. We can optimize logic, and there is a big number of iterations that has to be done before we go on a closure with a complex design. But then functional bugs have to be taken into account, and then both the front end and back end, they have to interact with each other to make sure that the specifications are met. Another super important topic here is verification. Just to give you some idea, if the system is not verified for all the states that it can be, it could generate an error. I give you an example. For example, one of my colleagues had this project with BMW a few years back, where a number of cars have reported sudden stopping in the road because there were an unknown bug. And after they went through all the verification of the system, they realized the bug was because they didn't account for the case where someone would push the air conditioning unit both up and down buttons the same time. So if you simultaneously push those two, which was something that was not considered during the design time, the system would come to a halt. So verification is super important, because if we don't verify the system for some of the things like this in this case that have not been thought about earlier, this could generate problem later. And then, verification has to be integrated, not just, during the design time, but also post-silicon, to make sure that everything that we've designed for or we've thought of is actually implemented at the end. So both front end and back end of the design. the backend design has more aspects to it. We have to, a lot of times we are not stopping at the programmable logic. We may want to send this to fabrication, and sending to fabrication is yet another set of processes that the designers have to go on. They have to comply with the foundry processes, the timing concepts that are met in simulation. Sometimes they don't hold when actual design arrives, so there has to be margins and other elements that has to be taken into account. And the understanding of Verilog and system Verilog is again required, because that enables you to understand what has gone on when people optimize these big systems. Again, this is not a system that you could optimize by hand, that a physical design engineer could change. They have to understand what has been going on in that huge code compilation. The validation engineers, they are responsible to validate and test this circuit, both pre-silicon, pre-implementation in simulation, and also post-implementation. And these are just very few of the possibilities that are available. I showed you in the previous set some of the new systems when they actually integrated these within these platforms within the clouds, and that actually brings upon a whole bunch of new opportunities for people who know system Verilog and Verilog to contribute to the design and optimization of digital circuits. The next set will be talking about the evolution of the hardware description language and its usages.